Okay, so just talk a little bit about the workflow. So in terms of the capabilities of the software, so what we're covering in this short course is just a short subsection, but just so you're aware of all of the different capabilities of the ANSYS software. So we can do linear and non-linear analysis. We can do acoustics, where you look at sound wave propagation and you can look at noise levels. You can do rigid and flexible body dynamics. So this is simulating things like mechanisms. So if you're just interested in the movements of the mechanisms or the kinematics. So we can do explicit dynamics. So this is to do with crash simulations or blast simulations or events that are very, very short duration. So we can do composite structures as well. So things like glass fibre or carbon fibre. So a lot of structures these days are starting to be built of composite materials, and sort of optimising the layups for those materials. Rather than doing it as trial and error, you can do it as using simulation. So on the vibration side, so you can do modal analysis, or if you're doing a full time history analysis, you can look at how your structure responds in real time. So there's other things like thermal simulation, where you look at temperature distributions. You can also look at that coupled with a structural analysis as well, where you're simulating temperatures and displacements and stresses at the same time. So we can also do topology optimization. So if you want to optimize the weight of a part, you can have a simulation tell you where to remove material. So where there's not much stress in a component, or not much of that material is being utilised in carrying load, you can use topology optimisation to identify those areas. So in terms of simulation of failure, so we can do fatigue analysis, you can do buckling analysis, sometimes that's a failure mode, and you can also actually do crack propagation as well under a mode 1 type cracking, where you've got cracks that are sort of opening. Okay, so in any sort of FEA analysis simulation that you do, there's a sort of predefined workflow that you follow. So you normally need to plan what it is you want to achieve. Do you want to look at failure, or do you just want to look at stresses and compare those to failure? So that will dictate what sort of analysis you're going to do. So in terms of your geometry, so most of the time that will come from an existing CAD model, or sometimes it might be that it's already an existing component that you're analysing that's failed. So you might need to create that geometry, and worst case is you might not even have any drawings. You have to go and do field measurements to create a geometry. Okay, so once you have a geometry, you then need to set up your model. So sometimes that might require some defeaturing, as we call it, of your geometry. So you don't necessarily include every single detail that's in your CAD model. So some of them you can get rid of in terms of it not being significant for your simulation. Okay, so once we have a clearly defined geometry for simulation, we then need to mesh it with nodes and elements. So usually there's some work involved in putting more elements in certain areas of the model, and we'll sort of do 1 or 2 workshops on the meshing aspects of the software. Okay, so then the next step is to do a solution. So most of the time this just involves you pressing the solve button and then waiting for the results to come back. So making sure you've got your load set up properly, and then sort of sometimes tracking your solution as it's progressing. So there's not really much involved in doing that. So once your solution is complete, you then need to review your results. So most of the time you'll have some sort of idea of what results are going to be sensible results. So you just do quick sanity checks, like making sure your structure is deflecting in the correct way, looking at your reaction forces, making sure they balance your applied loads, and then just making sure your stresses aren't unrealistically high, especially if it's a structure that you've already got. If you're getting stresses of thousands of megapascals, then your structure more than likely will have fallen over. And if it's still standing, then it could be that you've got some mistakes with your loads and boundary conditions. So then sometimes you might need to refine your model. So if there's areas of high stress, you might need to focus more on that area of the model and do a finer mesh in that particular area. Okay, so in terms of our planning, so we need to decide what sort of analysis do we require. So are your loads varying with time? Or are they just static loads from gravity? So if you've got loads that vary with time, you need to decide whether you can do it as a quasi-static or whether you need to do a dynamic analysis. So usually that will involve doing a natural frequency analysis to find out what your lowest natural frequency is, and then just making sure that your loads aren't sort of close to that resonance frequency. So the sorts of results that we require. So this will sometimes dictate how you set the model up. Do you need things like contact pressure if you've got multiple parts? Do you need to account for any nonlinear effects? So things like material plasticity or large deflection effects, or if it's a shell structure, whether you need to include membrane effects. Can we ignore dynamic effects? So usually that comes down to if you can simulate a dynamic load with an equivalent static load. How quickly do you need your results? So that will generally dictate what level of detail you put into your model. So what degree of accuracy do you require? So if you need really highly accurate results, you might need to do things like mesh sensitivity studies. And probably the last one is FEA an appropriate tool? So you might be able to get away with hand calcs for a particular problem. So there's no point doing an FEA analysis. So a lot of people tend to just use FEA for everything because it's so easy to use. Well, it's not always an appropriate tool in every single situation. Okay, so in terms of whether you do an implicit or an explicit solution. So a lot of this comes down to the, if you like, the speed of the event you're trying to simulate. So something like a creep simulation. So creep is usually something that happens over months, days, or sometimes even years. So usually you simulate this as an implicit simulation. So things like metal forming, if it's very slow, you can do as an implicit simulation. So when you have significant non-linearities, that's a point where you can sometimes do explicit or implicit. So, so explicit really lends itself to things like events that are over in a fraction of a second. So events that take longer than that usually aren't, it's not computationally efficient to simulate events of durations of seconds or tens of seconds with an explicit solution. So if you look at how it's used in industry, so traditionally car crash simulations, high-speed metal forming, or explosions or bullet impacts, these are all done with explicit simulations. So industries that use it most are probably defence and auto, although Australia doesn't really have an auto industry anymore, but in terms of worldwide, that's the sorts of industries that use it most. And also, so basically anything to do with defence or homeland security tends to use it quite a lot these days as well. So they're typical sorts of uses for explicit. Okay, so in terms of simplification of our geometry or our CAD, so here we've got a piston assembly, or it's just an engine. So we're really interested in the conrod and piston assembly here. So we don't need to include things like the crankcase or the cylinder with the fins. So what we wind up doing is we basically take a representation of the cylinder. This is more just for visualisation, and you can see we've got contours of stress on the crankshaft. So the piston and conrod are just there for load transfer and more for the visualisation. So this just gives you a sort of in terms of going from CAD to simulation, and then the part that we're really interested in. So it's very difficult to apply the loads on just the crankshaft on its own without having those other parts simulated to simulate the load path. Okay, so the thing I meant to look at there. So bidirectional CAD associativity is available. So any CAD software that you use, if you've got parameters that define your geometry, so in this particular case I might have something that defines the conrod length. If this engine was just at design stage, I could change that length in CAD and then rerun the simulation with a minimal amount of sort of setting up again. So I set up the simulation first time, I change my geometry parameter, and then just rerun the entire simulation without having to worry about redoing things like connections in the model or mesh controls or contact definitions. Okay, so part of our model setup is defining our materials. So in most cases you'll be doing linear analysis, so there'll be materials available in the material library. So it's very easy to add non-linear material properties to the materials that are already there. It's just a matter of inputting the data. So some of the time that will come from tensile test data, or it might be data that you've actually done a physical test on separately, or it might just be material properties that are available just on the supplier's website. So you can also create your own custom material if it's not already there in the material library. Okay, so with some models we have multiple parts involved. So in order to get those parts to interact with each other, we have the concept of contact. So there's different interactions between the bodies we can define. So these are defined with the contact behaviour. So if parts are welded together, we normally simulate that with a bonded contact. So no separation allows for a small amount of a relative sliding between the parts. So these are what we class as linear contact. So we don't need to account for any change in the relative positions of the parts. Okay, so for sort of more complicated interactions, so here we've got a pin being pulled and it's inside a bushing. So for a non-linear contact, so we can have frictionless, frictional or rough contact. So all of these allow separation in the normal direction. So whenever you have a negative or a tensile pressure between your parts, they will separate. You'll start getting a gap. So frictionless contact allows sliding with no resistance. So you can have a change in, if you like, a change in status between your parts in the normal and sliding direction. So a frictional contact, you can define a friction coefficient. So this might be something that would be more realistic. So you can normally characterise the friction with the friction coefficient. So if it's, say, rubber on steel, you can normally look up handbooks or just do a bit of a literature search and find out what that friction coefficient is. So a rough contact is essentially an infinite friction coefficient. So if you want your parts to sort of separate in a normal direction but not slide relative to one another, a rough contact is more appropriate. So with more complicated non-linear models, because friction makes your model non-linear, because you have to account for a change in the contact area. So that's going to change your characteristic stiffness of your system. So it's one of the first non-linearities that you will most likely encounter. Okay, so when we set up loads and boundary conditions in our models, so these are sort of very easy to understand loading. So you don't have to do any sort of conversions to apply the loads to your structure. So things like a hydrostatic pressure, for example, just a standard pressure. So acceleration and earth gravity, rotational velocity, and then all your different sorts of supports as well. So you've got fixed supports, so you don't have to individually apply constraints to individual degrees of freedom. So there's sort of compression only supports, frictionless supports which are used to allow sliding on a face, and then an elastic support, which is not a totally rigid support. So it might be something that's sitting on soil or something. So you can simulate that quite easily. Okay, so you can also do joints to define motions between components. So if you've got a very complicated assembly with pins and hinges and everything, so you can simplify the model by excluding things like the pins or the hinges in the structure, and you can just define the interaction between the parts directly without including all of the physical detail. Okay, so in terms of meshing, so there's a lot of automated meshing in the software. So most of the time you'll need to alter the default mesh that's given. So you will know ahead of time what areas you want more detail on, so you can put more effort into applying more mesh in those areas. So here we've got three different structures. So we've got a shell mesh. So this is something that's quite thin. So it might be something like a vehicle frame. So we model it as shells because the parts are quite thin. So you can you normally need to de-feature the model to get it to a shell, and then you can apply just a surface mesh on the structure. So here we've got a wheel rim. So this is a solid. So you can't generally represent this as a shell type structure. So we're interested in quite detailed stresses on pretty much all of this structure. So you can see it's got quite a fine mesh on there.
Sorry to interrupt, Sam. Wouldn't some of those magnesium wheels almost be like a shell? Like they're actually relatively thin, given.
Yes, yeah, but normally you're after more detail than a shell model can give. So you do have that flexibility, but generally it comes down to the level of detail you want in your stresses that you decides on what sort of mesh type that you use.
So you're saying if you used a shell mesh on a magnesium wheel, say, that you would possibly get the right results, or it wouldn't be enough detail as to where the stresses are?
Well, for example, in the where the wheel nuts go in, so it's generally a non-uniform thickness, so you probably can't represent that with a shell. So you could use a mixture of shells and solids on the same model, but here in this case it's all modelled as a solid, but you do have the flexibility of mixing different element types together. So we'll actually do a workshop that sort of demonstrates that today. Okay, so the other structure is basically the same thing, meshed with hex elements and also tet elements. So hex elements for sort of very regular shapes is very easy to achieve. For more complicated shapes, generally need some work on subdividing the geometry. So in terms of efficiency, when I say efficiency, number of nodes used for a particular structure, a hex mesh is normally much more efficient. But most structures that you'll analyse won't have fairly regular shapes. So you compromise to some extent by using a TET mesh, so you have more nodes. It will take a little bit longer to solve, but you don't have to de-feature or subdivide the geometry to get a hex mesh. So it's a balancing act. So they'll both give accurate results. It's just that in terms of overall total time to get your result would be shorter with a TET mesh, because you don't have to de-feature your geometry or sort of turn it into a geometry that can be hex meshed. Okay, so in terms of criteria for a mesh, so once you have a mesh, there's certain checks that you can do that will tell you whether or not you'll get reliable results. So as the mesher is creating the mesh, it does some of these internal checks on its own, but there are times where you do need to do some of these checks yourself. So there's a thing, so one of the ones that I check is element quality. So when we do the run through, I'll sort of show you how to check that. So generally you want to aim for an element quality of 0.4 or above. So it's really just a measure of I like to think of it as how well shaped an element is. So if it's got a good element quality, it will give reliable results. So the other ones so there's all sorts of other ones you can check. So skewness is basically how warped or skewed the element is. So there's also a warping criteria as well. So this just defines how warped the element is. So unfortunately this won't show on the recording, but if this is a shell element, so if it's warped, it sort of doesn't stay plain, it's sort of twisted. So it's a bit hard to say in words, and also with this sheet not behaving how I want it to. So it's sort of like that. So your ideally shaped shell will have a 1:1:1 aspect ratio, and it will be totally flat. So if there's any sort of, if you like, warp on it, then that will not give you accurate results, because the way the element is formulated is for the calculation points which are inside the boundary of the shell. They're meant to be in plane with the nodes. So if they're not, they will give you less accurate results. And the further away they deviate from being a plane, the less accurate your results will be. Okay, so if you do have a structure that is shaped like that, you generally need to use a very, very fine mesh so that each patch is closer to being having no warp. Okay, so when we solve an FEA solution or an FEA simulation, so we basically just start with the equation of motion. So we have static, kinetic and inertia terms. So for a static analysis, we just normally take the Kx term here. So any damping or inertia terms we ignore. So if you're doing a full transient simulation, then you would solve this full equation of motion. So with a static simulation, so normally we assume that the deflections are quite small, so your stiffness will not change, and your force, we don't take into account that it's a time dependent. So we sort of simulate that as a quasi-static. So we sort of simulate it at discrete points in time if it's varying, or we're not really interested in the variation between intermediate points of applying a load. So if you go from 0 to a peak load, you're not really interested in what's going on at 0.5 of that peak, because it's a linear simulation. You can always scale your full result to get your intermediate results. Okay, so in terms of the type of solver, so normally you can leave this to the software to decide. So with today's modern computing, you've normally got multiple CPUs, so you can normally do a distributed solution, or you can do it as a shared memory parallel. So with a distributed solution, you normally split your model up into multiple chunks, and each CPU solves its own chunk of the model. And because they're solving together in parallel, that usually results in a shorter solution time. Okay, so for nonlinear models, you normally track your solution as it's progressing. So when we come to doing the nonlinear section, we'll talk more about what this graph with the two lines actually means. Okay, so there's two different simulations here. So one of them is just a static simulation, so it's not really deflecting that much. And our second one here with the animation is basically a seal being pushed through a gap. So this is, although it's sort of animating, we're sort of simulating it as a quasi-static solution. We're not doing this as a full transient. So here you've got nonlinear effects of the part coming into contact with itself. So the load path is changing as that's going on. And then there's also quite significant deflections as that rubber squeezes through that gap. So there's also quite large strains. So all three of the nonlinearities are occurring here. So contact status change, quite significant strains, and also significant shape change as well. So all three of those things will contribute to nonlinear effects for a simulation. Okay, so in terms of, I guess, some post-processing, so this bracket, so if we're applying a load at the tip there, that's not showing. If we're applying a load at the tip of this bracket, and we've got it supported at some holes on the bottom of this plate, so we would do things like track or look at the total reaction to that load, and then maybe do a moment reaction just to do a quick sanity check to make sure our results make sense. Okay, so most of the time, with the first simulations you do, will be quite an iterative process. So our starting mesh is the one on the top here. Okay, so we might find we've got some high stresses in the model, and we're not sure if that's coming about because it's a stress singularity or if our mesh needs to be refined. So in a second pass, because we're only interested in stresses in this local area, we do a local refinement of the mesh just in this particular area. So that gives us a bit more detail. And then we might also introduce large deflection effects in our second pass. So when you're doing more complicated models, you generally don't do all of the complexity right from the beginning, especially if you're just starting out doing FEA simulation. So once you have more experience, then that might be a bit of an easier process to do, putting all of your nonlinearities in there. But as a general recommendation, we don't recommend you do that if you're first starting out. Okay, so just a bit of information. So FEA is basically an engineer's tool. So it's just like the equation for bending of a beam. So both of those can be misused. So they both have underlying assumptions. So as an engineer or a user of the software, you need to understand some of those assumptions. So it's very easy to misuse. So you can easily get believable results, even though you're putting in sensible input conditions. So in terms of the sort of more complicated things that can be done with the software, so you have to understand that it's an approximation. So it's a bit difficult to see if you're further away from the screen, but this image on the top is basically a simulation. The image on the bottom is a photograph of the actual crashed train. So this was the train crash that happened in Sydney in 2003 or 4, I think it was. So the waterfall train accident. So LEAP was actually asked to do the simulations because at the time they didn't know how fast the train was going when it left the tracks. So we simulated the derailment of the train, and then the model was made more complex by turning the front 2 carriages into deformable structures. So because there was, I think there was 7 or 8 fatalities, and there was a colonial inquest, and the simulations were used as part of the court case. So this is sort of getting up to the higher level of complexity that you can simulate. So you can see that the sort of stanchion, I think it's called, that sort of holds the power line. So you can see that is where it wound up in the simulation, and it's got a very similar shape in the actual photograph there. Okay, so this is a case of simulation being used after the fact. So something has failed, and we're simulating it to find out what has led up to that failure. Okay, so although this is sort of the uses we don't really want to have to use it for. So normally you want to use it for designing parts to predict that they don't fail. So if they fail on the computer screen, not in real life. So that's where the software is heading to, and that's where it's sort of being pitched towards, rather than it being seen as a high-end tool that you had to have a PhD to be able to use. So that is no longer the case. Okay, so in terms of some I guess best practices, so obviously we can't cover everything in such a short space in time, but you have to have a realistic goal for your simulation, and then sort of plan sort of clear steps to be able to achieve that. So if you've got an end customer, just set realistic expectations. So some people think you can simulate quite complicated things. You can if you've got enough time, but you've got to set realistic expectations. So usually when someone wants to look at a very complicated failure, you generally have simulations that indicate if it's failed, not necessarily the actual failure itself. So although that is possible, it's much more costly and time consuming to simulate. Okay, so when you're de-featuring your geometry, so you need to be careful that you don't remove too much detail in your model. So try to use symmetry where you can, because it means you can apply more nodes and elements on a smaller part of your geometry and still get results that are as accurate as simulating the full model. So start with a coarse mesh in the beginning, just to get an understanding of how your actual model is behaving. Okay, and then you always need to verify your results in some way. So there'll probably be some part of the structure that you can do a hand calc of the stresses, and you can use that to sort of validate your simulation. Okay, so if you're using FEA tools, you'll be expected to have a basic understanding of the underlying workings, not necessarily the mathematical equations that go in there and how they're derived, but just how the software basically functions. Just so if someone questions you on how you've arrived at a result, or if they don't sort of understand why you've applied a boundary condition in a certain way, you need to be able to explain that. Okay, so just understand the benefits and also the risks associated with computational simulation. So the risks are you can get believable results. The benefits are you can simulate things that you can't do with a physical test. So it's don't be sort of too daunted by that. So it's highly likely that someone simulated something you're trying to simulate before. So you'll most likely be able to find some evidence of that being done. Okay, so that's the end of that presentation. So if there's any questions, I'll quickly take some questions. Otherwise, I'll quickly show the demo. Well, not quickly, slowly show the demo.